Let's begin. Welcome again. Hope you had a good weekend. A couple of announcements about exam 2. I posted the information on the Canvas main page, the front page. There's a section now on exam 2 with a study guide and the Q&A from last year. I'll be filling in the Q&A for this year this Thursday. So the interpolation piece has already been answered, so I have those questions. Some of you are still filling out the ones for regression. I think the due date is tomorrow. Please get those as soon as possible so I can sort out the questions and we can answer them in class, just like last time. Exam 2 is going to be the same style as exam 1. Qualitative questions, a few quantitative questions, simple calculations here and there. Make sure you understand the definitions very well, that you can write them or choose them from a multiple choice, okay, like the essay question types or multiple choice, multiple answers. You'll have the full session to answer the questions. Those with exam accommodations, I've already reserved everything. I'll send you information. I'll send information out when we get close to the exam. And yeah, that should be it. On Thursday, we will dedicate as much of this session, as the class as we can to answer your questions about interpolation and regression. Those are the only two topics for exam 2. Last week, I almost finished with regression. I left off with this piece where we are trying to linearize a nonlinear model. Apparently, many of you have already done this in the homework assignment, so you may as well just come up and teach the class today, or this kind of intro for the class today. So this was a similar example in your, this is an example similar to what you had in the homework assignment. You essentially take the nonlinear model, which in this case was e to the minus ea over rt. So a is the parameter unknown and ea is the other parameter. This is a nonlinear model. The parameters show up nonlinearly. The normal equations would have been nonlinear. It's always preferable if you can linearize a nonlinear model, do that, because you will be guaranteed a solution in the linear case. In the nonlinear case, you will be hitting fsolve and nonlinear root finding, and you might not be able to find a root, especially if you don't even know where to start, okay? So it's always preferable to solve the linearized version of a model if it's linearizable. Turns out there is 2 or 3 classes of general models for regression that you can linearize. The first one is alpha x to the power beta, where alpha and beta are your parameters, or alpha f of x to the power beta. And you linearize this by taking the logarithm, whatever logarithm you choose for to knock out the exponential. So you can do base x or whatever base logarithm you want, so that you can naturally expand, split out that logarithm. So you get ya plus beta x, right? You reassign the names. Now this one is really interesting because that's also shown on, that's also one of the problems in your homework assignments, where your model has alpha x over beta plus x. And alpha and beta are the parameters. X is your independent variable. Now, to linearize this, you obviously cannot cancel with x and split that summation. If only you could split that sum, right, you could linearize it. But unfortunately, the sum is in the denominator. So we need to make that sum in the numerator, so we take the inverse of this. So if you take 1 or the reciprocal, which is equivalent to the inverse for an algebraic case. So if you take 1 over y, you get beta plus x over alpha x, and then guess what? That summation in the numerator now can be split. You get beta over alpha x plus x over alpha x, and x cancels out, so you get 1 over alpha, right? And then this becomes a new parameter, b, and 1 over x is redefined as your new independent variable. Remember, this is where your data is coming in. X and y are where your data is coming in. So your data is going to be provided to you as x and y values. To run them in this model, you have to take their reciprocals. You take 1 over y and 1 over x, and you plug this in. If you have a 0, for example, in the data, just get rid of that value if you want to do the regression this way, okay? So there's an example like this in your homework assignment. So use this approach, and I guide you in the homework assignment, tell you take the reciprocal, but that's just how it works, okay? Just simple reassignment, okay? There's a lot of supplemental material over here that's not required for the exam, but for those who want to do more, I have a full derivation of the normal equations. It gets pretty nasty with like some nasty vector calculus and stuff like that. So, and you get to see the full derivation of the normal equations there in the PDF. And if you have questions, let me know. There's also some additional reading material also for your own benefit in the directory for regression, in the files directory. Like, for example, you might ask, why are we using least squares? Why can't we just take the absolute value of the error? Why do we take the square? Why not the cube? Right? There's a big theory behind why we choose the square of the error as being the best indicator of an error, right? So that's all discussed. There's a document there that discusses all of that, why you're always guaranteed a minimum when you do regression. Because when the conditions we put to minimize S, those also could maximize S. When the derivative is 0, both at a minimum and a maximum. However, in regression, when you do the least squares, you're always going to get a minimum. And you can prove this using the Hessian or the second derivative test. And it's always the case for regression analysis. You're always guaranteed that the parameters you solve for when you solve the normal equations, they're going to give you the minimum. Okay? And with that, we are done with regression. So we are done with the unit on what I call elementary data analysis. Truly, a full data analysis would require us to jump into more statistics and perhaps do neural networks. We're not going to do that this year. We don't have time to do it. At the end of the lecture, at the end of the class, I will have a colleague of mine come and give you a lecture about how to build neural networks. So it will not be on the exam, but it will be for your own benefit, for fun. You'll build a neural network with her live in class together in your Jupyter notebook. So that's always been a success in this class for those of you who are new to neural networks. So we'll do that at the end of the class. Now, we're done with the unit on data analysis. So if you remember, we had this, at the beginning, we had this orphan subject on errors and numerical methods. It didn't fit into any overarching story, right? Then we had the unit on solving algebraic equations. We solved systems of linear equations, single nonlinear equations, and systems of nonlinear equations. And we did that at the beginning because those show up in everything we've done afterwards, right? Then we talked about data analysis. We did interpolation and regression, how to represent points. You interpolate between them or put a model. And I know many of you have questions about the difference between regression and interpolation. I'll address those on Thursday in the Q&A session. The next subject is going to be solving differential equations. So we know how to solve algebraic equations. We will learn how to solve differential equations. We will focus on ordinary rather than partial. We'll touch on partial a bit. But there's one other orphan subject that I want to talk about because it is kind of necessary. It doesn't fit in with data analysis. Maybe it fits in a little bit in data analysis, but it's kind of its own thing. And there are actually just 2 chapters that I can cover usually in just 2 lectures: numerical integration and numerical differentiation. Okay? So you could say numerical integration fits into data analysis if you have a bunch of points and you want the area under the total number of those points. Sure, but we're just going to call them an orphan subject. Numerical integration, numerical differentiation. Numerical differentiation is going to be very important for ODEs, so I'm going to put that under solving differential equations as a prerequisite. So let's go ahead and get started on numerical integration. I don't have a fun story for this one. Sorry, I'm out of stories, but maybe we'll start. Here's an example to evoke some emotion. Apparently, so the school of thought that I come from with education and pedagogy is something is more likely to stick in your mind if it evokes an emotional response. Could be a joyful response or a response of So a disaster, for example, or a positive success story, both of those are more likely to stick in your brain. So those are the examples I try to find, but they're hard to find on all specific nerdy subjects. But this is the best I could do for this one. This plot shows a scatter data of metric tons of CO2 emitted per capita worldwide. So this includes the entire world, all nations, right? Versus year. So in 1960, per capita, we had about 3.1 metric tons of CO2 per capita worldwide. And then, as we industrialized and started producing more and more power, et cetera, and burning, we increased, and the world became more industrialized. And then we hit a little snag in the 80s, comes down. We discover cleaner burning fuels, et cetera, and oscillates, then jumps up, then comes down in a cycle, right? So, there's values over the years, right? It's from 1960 till 2012 or 2015, whatever that number is, all right? So now, if you were asked, how would you calculate the total, given this data, X and Y values, okay, year and metric tons of CO2, how would you calculate the total emissions of CO2 for those, 4 or 5 decades? Give me an idea. Okay, so you're suggesting, so what would be the benefit of the interpolation? Okay, so you'd have an exact formula that you know how to integrate analytically, and you find the answer, okay? So let's say total CO2 emissions per capita over the entire, so I want the area under this curve, right? That's what that question is essentially asking. What are the total CO2 emissions per capita in those 50 years? So how would you sum that up?
You could just add up the Y values at each point, or you could just do a regression and find the general formula and then integrate over that.
Okay. And what's the advantage of having a formula? Is that you can probably integrate it exactly, right? Just like your colleague said. Okay. Any other thoughts? Yeah, you're not wrong. Okay, you're not wrong. And those ideas are actually the foundation of, well, what I'm happy with is that you try to use what we learned so far, interpolation, regression, to try to solve this problem. And you're not entirely wrong. I'm gonna add a little twist to it to further clarify specifically what we're gonna do with interpolation. Aaron, right? So what your colleague said here is we interpolate the data, but do you think you're gonna interpolate the entire data set? No, so you'd interpolate over a few points, right, and integrate that analytical formula. And this is exactly what we are going to do. This is the foundation of what we call the Newton quotes formula. I'll discuss that in detail. Or we can just add up the individual values, like your colleague said here, and call it a day, call it a victory. And that's fine. That's going to be a little less accurate. And we'll see the error between all of the different methods. So at the end of this chapter, my hope is that you'll be able to define what quadrature and numerical integration means. Hint, hint, they mean the same thing, okay? Because we're going to solve the numerical integration problem with quadrature. I'll define where that word comes from. It comes from an ancient word where they used to, they wanted to trade land. That was important to humans. It still is to some extent, especially like in farmland. So to measure the area, they would split it into small pieces and measure the smaller areas, little triangles or rectangles. That procedure is called quadrature. Okay, so we're going to do the same thing on the area under this curve. Calculate the area under an analytical function using Newton quotes formula. So many functions can be integrated analytically, like by finding the antiderivative, and many others cannot be integrated analytically. Okay, you have to do some fancy math on them, or like there's no actual antiderivative for that. You cannot really integrate the function. So the only way is to solve it numerically. So we were going to take an analytical formula and function and integrate that numerically. Calculate the area under a discrete set of data points, also using Newton quotes formulas. Use the left point, right point, midpoint, trapezoidal, Simpson's 1/3 and 3/8 rules to calculate the integral of a function. So given an analytical function, you're going to learn about 6, 7 methods to do the integration analytically, well, numerically of an analytical function. Determine which of the above formulas apply to equally spaced and unequally spaced data. So there's two competing things here, two things we're doing and that I want you to remember. The formulas we're developing are going to apply equally to integrating analytical formulas and integrating discrete data. Okay, so you will be faced with both things in practice. You might collect data from measurements and you want to integrate over the entire data set to get the total number. Then you're going to use some of those formulas. Not all formulas apply, to all discrete data. Okay, so that's the challenge. So the formulas will definitely apply to analytical functions, but not all the formulas are going to apply to discrete data, and that becomes clear as we do more examples. And finally, I have a slide about the error bounds. We're not going to derive the error bounds. It's very complicated to derive them, but I'll show you what those bounds are, and you will see they're going to be a function of the interval size and how many subintervals you create in that interval. All right, so let's dive in. The mathematical description of what I've been talking about is find the area under the red curve between points A and B. So given some function, f of x, shown in red curve here, calculate the integral over some finite region from A to B, right? So that is equivalent to finding the area under this curve. We will use a special method of numerical integration. They're all kind of equivalent with each other. I really like the Newton-Cotes integration formulas. And the idea is pretty simple, is that the approach is to approximate f of x as a polynomial, because polynomials are very easy to integrate analytically, whereas not all functions, complex transcendental functions, cannot be always integrated analytically. All right? So we take a function, we approximate it as a polynomial. All right? We'll talk about the details, how many points, etc. We approximate it as a polynomial and then perform the integration on the polynomial, because it's very easy to find the antiderivative of a polynomial and just solve it numerically. So the procedure will be we first choose the order of the polynomial. This determines how many points are needed to find the coefficients of the polynomial. So you could approximate f of x as a straight line. So you'd need 2 points, maybe a and b for sure, right? You might approximate f of x as a cubic or a quadratic. You need 3 points. So you might choose the point in the middle between a and b, or somewhere at another point, right? And so on and so forth. So that's the standard procedure. Once you choose the order, you choose the points where you want the polynomial to go through. Remember interpolation. So essentially now we're artificially choosing points, and we're going to weave through them a polynomial and integrate that polynomial analytically. And then integrate the polynomial exactly on the interval in question. All right. We will start first with the left, right, and midpoint rules. They all fall under the same concept. And this concept is that the simplest polynomial approximation of a function is a constant. It's the worst, but you see it's going to work like magic. Okay? There's a trick to make it work like magic. But the simplest approximation to a function is a constant. F of x equal some constant. And then if f of x equals some, I haven't told you how to choose that constant yet. Okay? Now, if f of x is a constant, then the integral, the approximation of the integral of f of x between a and b, if f of x is approximately a constant, that constant pulls out, and you get b minus a times that constant, right? It's essentially the area of the rectangle and under that curve, right? Okay, so we can choose that constant in a number of ways. I will show you 3 ways to choose that constant. All right, so let's take this curve. We're integrating that red curve between a and b, so we want the area under this red line between a and b. The first approximation is I'm going to choose the left point, or f of a, as the constant. So I'm going to approximate f of x on that interval. So the true f of x is that red curve. I'm going to approximate it with the value f of a. So it's going to be that blue line, right? over that entire interval. We're saying that function, I don't care how it behaves. I'm just going to treat it as equal to f of a at all of those points between a and b. Then this amounts to saying that your integral is equal b minus a times f of a. And that's called the left point rule, because it's choosing the value of f at the left side of the integral, f of a, right? That's called the left point rule. Very simple. F of a times b minus a. Okay? Now you will say this is a horrible approximation. Absolutely. Unless the interval is very small. Okay? Unless the interval is very small. And I will demonstrate that to you as we proceed through the lecture. Okay. Now what's another way to choose a constant? Really, you can choose any arbitrary value for that constant in that interval. Another value that kind of seems to make sense is to choose f of b. So rather than taking f of a, we're going to choose f of b. We're going to approximate that entire red curve between a and b as f of b. So you see that blue horizontal line. Everywhere between a and b, at every point here, I'm approximating f of x as equal to f of b. No questions asked. Just a constant value over that entire interval. Then the integral becomes b minus a times f of b. It's kind of like silly, right? Like, well, what are we learning here? Just bear with me. Okay? So that's called the right point rule, because you're approximating the function using its right value on the interval. Okay? Left point rule, you choose f of a. Right point rule, you choose f of b. But you say, you know, why not choose some point in between? Right, like a plus b over 3. Or, you know, one obvious choice is the midpoint. Because that's like, you know, that's an equally valid between all possible choices. We can choose the point in the middle. If you do that, then you would be approximating the entire function by that blue line, that value. And you see, kind of, it tries to, for a function like this, it overshoots on one side and undershoots the function on the other side. It overpredicts on one side and underpredicts on the other side. So in a way, it's like trying to compensate. Compared to the, if you go to the left point rule, it's underpredicting all of those values here, right? And if you go to the right point rule, it's overpredicting all of those points on this side of the interval, right? It's over-predicting all of those points. So the midpoint rule for a function like this seems to be a better choice, right? Because in a way, it overcompensates and undercompensates, and that effect will essentially just cancel. Those two effects will cancel each other, and you're going to get a better approximation. Okay? So that's kind of the argument behind the midpoint rule. Turns out that it's about the same error as the left point and the right point rule. It's no better than choosing the left point or the right point, okay? But that's called the midpoint rule, all right? Now, I'm applying this for an analytical function. Okay, before we get to discrete data, I want you to think for a minute. If you have discrete data given as f of a, f of b, f of c, f of d, et cetera, which method is going to be easier to apply on discrete data? Left point, right point, or midpoint rule? The midpoint rule requires knowledge at a point at the midpoint, which you might not have in discrete data. Unless your data is equally spaced, you can jump every other point, and you say, this is my midpoint, and I can approximate the function with that midpoint. But if your data is not equally spaced, you don't have information at the midpoint. Even if you interpolate, you're not creating new information when you do an interpolation. So left point and right point rules are better for discrete data. And we will cover that once we get there. Now, before we start testing those in practice, I also want to show you how we do this in Python with a built-in routine, because obviously that's what you're going to use after you're done with this class. Okay, but at least I want you to be engineers, not technicians, okay, to know what goes behind the scenes. And also I want to compare what we are implementing to something that is very accurate and already exists in Python. So for continuous function, SciPy has a module called integrate. And from integrate, you can call the function quad. Quad stands for quadrature. Okay, so you say from SciPy import integrate, and then you call integrate.quad. That's the quadrature subroutine in SciPy. And you give it a function name, just the name of your function that you're integrating, e to the minus sine x squared. Right? You just give it the name of that function that you're integrating and give it the interval a and b. And it numerically does its magic. It's a very accurate algorithm, uses some advanced methods and does some optimization to get a very accurate value. So we are going to use that to compare to what we are learning. Left point, right point, midpoint, we're going to learn more and more tools. Technically, it uses what's called adaptive Simpson's quadrature. We're going to learn Simpson's method by the end of the lecture. Okay? All right, so right now we have these three formulas. Left point rule, it says the approximation of the integral of a function if b minus a times f of a. Midpoint rule, b minus a times, right point rule, b minus a times f of b. And midpoint rule, b minus a times f of a plus b over 2. All right. Now you're going to get your Jupyter notebooks, and we're going to develop 3 routines that implement the left point, right point, and midpoint rules on the function 1 plus half sine squared 1.75 pi x on the interval 0 to 1. Okay, so we're going to implement those 3 routines. We're going to solve that integral numerically with those 3 routines. And then we're going to compare to quad and see what answers we get. All right? So grab your notebooks and give it a try while I do the same here. Let me move the slides so you can see them. Window. Okay, so you're developing 3 routines, 1 for the left point, 1 the right point, 1 for the midpoint. Your routine should take any function. In this case, you're going to give it this function, 1 plus 0.5 sine squared, etc., 1.75 pi x. And you're going to integrate that numerically with one of those routines. Oops. With one of those routines. Let me just open it again. Sorry. Okay. Grab your Jupyter notebooks, and let's work on this together. Have a notebook already here. All right. I'm going to create a new notebook. Numerical integration activities. All right. So I'm going to import my boilerplate stuff, and I'll just copy it from another notebook, NumPy, matplotlib. I don't need scipy.optimize. I hope you already have those kind of typed up in some notebook for those in the back. Oops. Where is it? Okay. You good in the back? All right. And I also want to import from SciPy, import integrate. You can import integrate.quad. I just import integrate, and I always call integrate.quad. There might be other routines in Python. I want to make sure this is coming from SciPy. Okay. All right, so the first thing I want to do is get familiar with this function. So when in doubt, print it out. When data is at hand, plot it to understand. When a function is at hand, also plot it to understand, okay? Or if you can come up with a better sentence, we'll put it on a T-shirt, and I'll give you that T-shirt, okay? 1.1 plus half sine squared. I'm going to define my function, and that is going to take some value x, and we're going to return 1.0 plus 0.5 times p dot sine 1.75 times mp dot pi x, right, squared. 1 plus half sine squared 1.75 pi x, right? So that's my function. Let's plot it. X is mp.linspace. And let's go from 0 to 1. That's what the interval is, right? The interval is from 0 to 1, so I only care about the function between 0 and 1 right now. And plt.plot x, my function f of x. Okay, looks like that. Okay, so I'm going to do now some gymnastics here. You don't have to worry about that, just to show you more of, I'd like to fill in the area under the curve. So here's a little trick to do that. If you do the plotting approach like I do, which is not the best, but it does, it gets the job done. So if you get, I want a reference to the axis, and then there's a function called fill between. Again, this is extra stuff. You don't have, you can ask GPT to help you with that if you want. Or my function of x, right? And I want to fill in edge color is k, and face color is. You don't have to type this if you. Let's see, light gray, and line width equal 1. Okay. Oh yeah, look at that. Okay. So I'm filling the area under this blue curve from 0 to 1, right? So that's what we're trying to calculate here. Okay? That's what we are trying to calculate. Kind of nice to see it visually. Okay. So now you can see if we use the left point rule. Okay, let me lower it a little bit so I can reach it. Okay. If we use the left point rule, well, the function kind of varies quite a bit, between like 1 to 1.5, then comes down to 1, then goes back. If we use the left point rule, we're going to approximate all that blue line with just a single value here, right? So we're going to get the area of this rectangle. So we are going to underestimate the area under the curve. If we use the right point rule, we're going to be at about 1.2. Okay, so we're going to underestimate here, overestimate, underestimate, overestimate. Might balance things out. If we get the midpoint rule, we're going to be here in the middle. So we're going to be mostly underestimating. Okay? That's kind of what to anticipate. All right, so let's do it. Let's define left rule, function f, a, and b. And I'm going to return b minus a times f of a. That's the left point rule. F is some arbitrary function. Just give it the function name. Def right rule, also f, a, and b. And we're going to return b minus a times f of b. And finally, define midpoint rule, f, a, b. Right? That's the minimum I need to compute these rules. I need the name of the function and the bounds of the integral. The lower bound and the upper bound, a and b, call them. The midpoint rule, return b minus a times f of a plus b over 2. All right. So let's see. Print left rule, my function a, b, or 0, 1. 0 to 1. Oops. And then print right. Now see the values, print right rule, and print midpoint rule. Okay, look at that. Give me 3 different values. For the left point rule, the area was 1. For the right rule, the area was 1.25. For the midpoint rule, the area was 1.07, almost like the left point rule. Indeed, as we anticipated, because the midpoint rule just kind of is going to underestimate everything like the left point rule does. All right, let's see a value that is closer to the truth. And for that, we are going to use quad. So that's why we learned about quad. All right. So I'm going to call integrate.quad. Okay. And if you look at the function signature, see a bunch of things, computes a definite integral from A, integrates function from A to B. Okay? So we're going to go and call my function here, my function on the interval 0 to 1. If we do this, we get 1.27 with an error of 10 to the minus 12. Okay? So of those three rules, the right rule was closest to the more accurate value. Indeed, because it was underestimating a little bit and overestimating a little bit, so the errors kind of cancel out. But the point is that neither left point, right point, or midpoint rule, or any one of them is better than the other. It depends on very highly on the function. Okay? But we're still committing quite a bit of error with the left point rule. It's a huge error. Same thing with the midpoint rule compared to a formula that is very accurate. Okay, so I'll give you a minute to catch up. Do we all have the same answers? Great. Okay, so how do we make these silly little formulas more accurate? Well, it's kind of like we approximated the function as a constant on a huge interval. But if the function is continuous and analytical, right, why not take that big interval and split it into many, many smaller intervals where the function is really approximately a constant, right? If you shrink the interval small enough, any function is almost nearly a constant. And because the function is analytical, we can define it over any kind of smaller interval. So that's the idea. To increase accuracy, we can take these formulas and apply them to smaller and smaller segments on that A and B. So we're going to take A and B, and we are going to artificially split it into smaller segments, smaller and smaller segments, like I show here, and then apply those formulas on the smaller segments. And then they're going to be way more accurate. And intuitively, the more segments you have, the more accurate you are going to be, right? So although those formulas were so, at face value, they looked so rudimentary, they're not. Their true value occurs in the power of large scale, essentially taking that interval and splitting it into thousands of smaller segments, and then applying those silly rules on the smaller segments, and you'll see how your accuracy is going to skyrocket. But this is going to require a little bit more legwork. Now, this procedure of taking a large swath of land or area and splitting it into smaller areas, that is called quadrature. That's it. Okay? We also call it a composite rule. So when I say apply quadrature using the left point method, I mean split the interval into smaller intervals and apply the left point on each one of those smaller intervals. Or if I tell you apply a composite left point rule, I mean take it and split the interval into smaller intervals and apply that left point rule into each one of those smaller intervals. And so the idea would be you take that interval from A to B, you split it into n plus 1 points or n segments, right? So there's always one less segment than the number of points. And then evaluate the area of the curve for each segment. And now you see how, like this would be the right point rule. You see it's kind of, although it overestimates and underestimates a little bit, it's a very small error compared to what we did previously. So I predict we're going to have way more accuracy if we do this now. It's going to require a little bit more programming. So let's go ahead and do that. Develop a Python code that computes the integral analytical function with an arbitrary number of segments. So now our left point rule, our right point rule, or our midpoint rule is also going to take one additional argument with it, the number of segments. Okay? To say, I want you to evaluate the left point rule with 100 segments and get me the answer for that integral. All right? So similar to the Taylor series, how many terms? Now we have how many segments. Right? So let's just do this together. Right, so this would be activity, what, 2? Okay. So I'm going to call these composite rules. Okay. I'll call these composite rules. So def composite left rule. It will still take F, A, and B, and we're going to give it a number of segments, N, to determine how many sub-intervals, how many segments we're going to split that space. Okay. So now you have A and B, and you want N segments. Remember, N is the number of segments, not the number of points. N is the number of segments. So if using linspace to create those points in the interval A and B, I mean, there's nothing better than linspace to give us equally spaced points on that interval, right? So we need to create N plus 1 points with linspace to get N segments. If you want 5 segments, you need 6 points, right? If you need 100 segments, you need 101 points. So we will use linspace. I'm going to create a segmented sequence of values, np.linspace, going from A to B with N plus 1 points. Remember, N is the number of segments. I need N plus 1 points. If you mean by N the number of points, then you need to adjust that in your linspace and figure this out. All right. Now my integral, now I need to loop over each segment and compute and apply the standard left rule to each one of those segments, right? I'm going to go over the first segment, apply the left rule, get and add it to the next segment, add it to the next segment, and so on. So I need a for loop, and I need a variable to store my result in. And I'm going to call that result equals 0, because we're just adding to it. We're going to add to 0. And we're going to loop. We're going to use the range function and some index for segment S, let's say, in range going from 1 to N. Okay. And then for each segment now, for each segment S, okay, your left point for the segment is XS, and your right point for the segment is XS plus 1. So if you go back here, this is it, right? So this is your first segment. I'm taking X1 and X2 as my bounds for that segment, and I'm going to apply the left point rule only on that segment. Then I'm going to go to the next segment and take X2 and X3 and so on, right? Xi to Xi plus 1. So maybe I'll call this I. Let me call it I, because I used I on the slides. Okay. Now you have A and B, and then simply do the integral and add it to the result. It's B minus A times f of A. And once you're done, return result. Actually, I should start from 0 here, right? Yes, we should start from 0. Sorry for the typo. So we should start from 0. All right, now do the same for the right-hand rule and the midpoint rule. The only thing that's going to change is this formula over here. Correct? The only thing that's going to change is that formula. So you can just copy paste and call it composite right rule. The only thing that's going to change is here, f of b. And finally, the composite midpoint rule, you will have f of a plus b over 2. OK, so now let's try to execute this. Let's say we just pick 100 segments and say composite left rule for, let me rename this, composite midpoint. So composite left rule, I'm going to give it my function f, my function. And we're going to do from 0 to 1 with 100 segments. And I'm going to print the result. And we'll do the same thing for the right rule. And for the midpoint. Okay, I'll go back up here for a second for those of you who are still trying to catch up. There you go. So I'm assuming you already got the left rule. You just copy and paste, change the name of your routine, and change the formula for the approximation. What we're doing here is nothing fancy. We're just taking that interval and B, splitting it into smaller intervals, and applying that very low accuracy formula on each subinterval. So we're artificially increasing accuracy by applying it over more intervals, which is pretty smart, frankly. If you have those, go ahead and evaluate that function, the integral, and compare it to quad. Did any of you do that already? What did you get? You get closer to the right answer? Yep. Try to increase the number of intervals, like put 1,000 segments. Okay, so if you remember, the true answer was 1.273, okay? So let's do this here with 100 points. Look at that. We're getting pretty close with 100 segments, sorry. Let's do 1,000. It's going to get even better and better and better. Look at that one. The midpoint rule is nailing it. It's awesome. The midpoint rule is getting it right on, right? Followed by the other two, right? So it does get more and more accurate. So that silly little formula to approximate the function, when I said I want to approximate the function as a constant, I saw many eyes squint at me. But lo and behold, this is amazing, right? Again, you have to don't suspend your mathematical thinking, but allow it to be flexible because we're doing numerical methods. We're doing approximations here. Okay? That's pretty cool. Those are like the simplest integration methods. Yes?
Can you explain again what the integrate.quad does in relation to this?
Yeah, so integrate.quad, think of it as a black box, high accuracy integration, numerical integration routine. That's all you need to know. It doesn't do midpoint or left point, etc. It does something fancier called Simpson's rule, which we're going to learn, but it also does it adaptively. So what that means, more accurate, but specifically, it has to do with this number of intervals. How do you know the number of intervals? So quad, what it does it kind of by trial and error. It says, okay, if I do 100 intervals or 110, am I increasing accuracy? What is the best number of intervals that is going to give me accuracy? And not only that, it adapts, it does variable size intervals. In some spots where the function is nearly constant, you don't need 10 intervals. You can take one interval, right? So it does all of that behind the scenes. Okay, it's very smart about it. But it's not too far from what we're doing here. This is pretty cheap still, okay? So use quad in practice, or use one of those, it's up to you. But at least you know the mechanics of it. So what quad is doing behind the scenes is nothing fancier than this. All right? We'll learn the Simpsons method in a minute. Okay. Let's proceed. All right. So that is called quadrature or a composite method. When we say this, when I say quadrature or composite method, that's what I mean. Okay? All right, I'll show you the code, etc. Now, the next question is, what about discrete data? So we started off by talking about CO2 emissions, right? Sorry, those slides are very annoying up the front. Oops. Okay, it's a little bit better. Like these lights up here is just like, I can't see anyone in the back. Okay, so what about discrete data? We did this for a continuous function where we could evaluate f of a plus b over 2. You could evaluate f at any point in that interval. But for discrete data, you don't have that luxury, right? Your data is already specified for you. The intervals are already specified for you. So you will be given data like this. And this is equally spaced data, but you're given, equally spaced in this case, let's say. Okay? So now the question is, which of these methods apply? The left point rule, it applies immediately. Because you choose the left point, you take the first interval, choose the left point value, multiply it by, calculate the area and move on, right? So for each interval, for each segment, you take the left value, you draw that rectangle, compute the area, add it to this one, and so on, right? The right point rule also applies readily. You take the point on the right discretely, right? You just take the value on the right in the array and multiply it by the distance, and you get that rectangle, and you can add them all up. And it doesn't matter if the intervals are equally spaced or not, because you're treating each interval separately, right? It doesn't matter where the intervals are, how big they are, how small they are. Okay, now what about the midpoint rule? Does it apply to discrete data, and under what conditions? Think about that while I figure out the lights. Bad. Good. Okay. Okay. What about the midpoint rule? Think about it. You're like anxious to give me the answer.
I don't know if it's the right answer.
It doesn't matter. Let's think about it. That's the point, right? So what are you thinking?
Well, if you take the distance between x1 and x3,
Uh-huh.
the height of x2, it's not quite the same as the midpoint, but it's a midpoint between 2 points. Then you can do x2 and then x4 with the height of x.
It won't be necessarily the midpoint. So if they're equally spaced, then that works. It is the midpoint, right? So if this interval is of the same size as this interval, then this is indeed the midpoint, right? It's indeed the midpoint, and you can apply the midpoint rule. But it's a programming nightmare. Well, not a nightmare, right? Because you have to skip every other data point, right? What about unequally spaced data? It's not the midpoint anymore. It could be the 1/3 point or 1/15th point, right? It's just some random point in between two other points. So really, the midpoint rule or whatever other point in between rule is hard to apply on discrete data. So on discrete data, from the methods that we learned so far, left point, right point, and midpoint, the left point and right point rules are readily applicable on equally spaced intervals and unequally spaced data, okay? Because you just take either the left side of the interval or the right side of the interval. Okay, do I have it? A little midpoint rule can be applied to equally spaced discrete data, but you must take every other 2 intervals at a time so that the midpoint can be defined. If it's not equally spaced, the midpoint rule cannot be applied, right? And then you'd have something else, the 1/3 point or 1/4, who knows what accuracy that is. Will it work? Sure, but it's not something that is commonly used, right? Okay. Now for discrete data, you cannot use quad. Okay? You cannot use integrate.quad because quad is made for SciPy. If you haven't noticed already, SciPy is more focused on continuous functions and things like that, doing numerical things on continuous functions, solving a nonlinear system of equations, right? Optimizing with regression, or a model, right? Curve fit, and quadrature. But it doesn't do it on discrete data. For discrete data, the built-in routine in Python that we will use is called trapz, and it comes from NumPy. Trapz, it's not a trap. It stands for the trapezoidal rule, trapz, for trapezoidal. And we will learn that next. But that's what we're going to use right now and treat that as the truth. The trapezoidal rule is a very accurate method, and it works very, very well for discrete data. What it does behind the scenes, just bear with me. I just want to use a method that gives me a different answer than the methods that we have learned so far, so I can compare. And it only takes 2 arguments. Because it's discrete data, it takes y values and x values. There's no function. The function values are built in the yi values, right? So there's no f, a, and b. It's just yi and xi. Okay? So now using the left point, right point rules, develop a Python code that integrates discrete data, apply it to calculate the world emissions of CO2 per capita, and compare your results with the TRAPS-V routine from NumPy. Now you will need to download the data called CO2 world emissions.txt from Canvas. So go on Canvas. Go under modules or under files. Under modules, it's very easy to see it. There's an integration module, and there's a txt file there containing data. X values contain the year, and Y values contain the metric tons per capita worldwide. Did you find it? If you didn't find it, just share it on Discord.
What's the name of the file?
World. So it should be the only data file in there. It's called world CO2 emissions.txt. CO2 world emissions.txt. Yeah, if you search maybe in Canvas, you can find it. It should be under files. Easiest way to get it is through the modules. Sorry. Just trying to figure out these lights. Oh. Look at that. I can stop. Okay. It's like there's just random buttons here with no indication of what they do. Okay. All right. Just do it like this. Enjoy the relaxing time. Now focus on my voice and enter into a programming mode. Let me see if I can work with these lights here. These ones I want off, these ones I want on. Yes. Okay, let's do it. Sorry for the distractions, but these were very, very annoying. Okay. Let's see, where am I? Okay, so now grab that text file. We didn't deal with text files or reading data from files. You might know this from your stats class with fancy pandas, whatever. We don't need any of that. We can just use NumPy to load up simple data. And so if you put that data file next to your Jupyter notebook, there's a little routine in NumPy. So let's see, activity 3. Okay, and it's called numpy.load.txt. Okay, and you just give it the name of the text file, and this is going to be CO2. Do I have it here? Hold on. See, I might not have it. Nope. Let me move it to the right location. Sorry, let me move it. CO2. See now. All right, CO2 world emissions.txt. And to load this up, so if you were to look at the text file, it's just a separated file. You give it the delimiter, and that's a comma, and it loads up all the data. Now it shows an error. Cannot float. What the heck? Okay, let me just take one look. CO2. Okay. 1 second, just looking at the data file. P.load txt delimiter to world emissions dot txt. Let's see. Dot load txt. Oh, sorry, it's not a comma. My bad. It's just a space. Okay. Yeah. So now, if you look at the data, it's just got 2 columns. In the first column, there's year. In the second column, there's the value. All right. So here's what I'm going to do. I'm going to take the first column from the data and put it in as x values. So I do this by splicing. So data, I'm going to take all the data in the first. So I'm going to take all the values in the first column, all the row values in the second column. That's what this is doing. And then plot, plt.plot, xi, yi, scatter. And then you can add grid and whatever to make it more beautiful. All right, so those are the data that I showed you at the beginning of this lecture. All right, so now we are going to implement a discrete version of the left rule. So discrete left rule. So that's for discrete data. And all are x values, I and yi values. And so we're going to go through each interval that's defined by the data. I'm not defining those intervals. The intervals are already defined by the data. I'm going to take the first interval, do the left rule, second interval, third interval, and so on. So I'm going to store everything in the result. Okay. And then I'm going to take the size of how many points I have. x1, x2, x3, and so on. Because that is going to tell me how many intervals I have. If I have 10 points, I have 9 intervals, right? So that will allow me to do a for loop and go and access through all of those points. I'm going to do n for the number of points, and that's the length, the size of the xi or yi array. They better be of the same size. And again, if you're in doubt about this, create an array on the side, do n equal len x, just play around with it, print it to prove to yourself that this makes sense to you, okay? Or if you're trying to kind of figure this out, don't do it on the full data. Create a small array with 5 points and just play around with that. I always forget what range does. So I just do a little for loop and print, and okay, now I remember what range is doing, okay? Now I can loop over all the segments. So if I have n points, I have n minus 1 segments. Okay, so my loop is going to be over the segments for I in range from 0 to n minus 1. Okay, so that is going to give me exactly n minus 1 segments because range is open, right? It's going to go from 0 to n minus 2, so that's n minus 1 segments, exactly. And then simply do A is xi. That's going to get, for the ith segment, the left point is xi, the right point is xi plus 1. Sorry, Devin. Your neck is going to get taller now as you're trying to read this. You can put some more stuff here so you don't see better, sorry. Nobody uses that screen, by the way. Like, right? It's like a silly setup. When they first assigned this class to me, I call them like, I can't teach in this class. It's like way too big for 50 students, and I'm like, I have to walk a mile to get to the slide. It should be in the middle. So anyway, we usually don't hold this class here. We do it in Warnock. There's a classroom for me. It's very nice setup, etc. Anyway, but I let it pass this year. So, but I gave them a hard time still for people at the. Can you imagine scheduling classrooms? Like what a nightmare job that is. I don't think there's even code that could solve that problem. It could be a nice homework assignment that's open-ended. You just go figure it out.
That's crazy.
Okay, so now we have the interval. In other words, the length of the interval. So that's, if you're thinking about that rectangle, we have now that little width. We need the height. For the left point rule, the height is f of a. Okay? Now, we don't have a function, but we have y values. So the y value that corresponds to the left side is going to be yi, not yi plus 1, right? Because we're indexing to the left. Okay, so segment 0 starts at x0 and x1. So the left side is xi. So segment I, the left point is xi, the right point is xi plus 1. So yi is the value of f of a. So I'll call this fa, and that's going to be yi. Just an array. Then finally, result, b minus a times fa. And then return the result. Same thing for the discrete right rule, except now you're doing fb. So you're taking the right side of that interval. Okay, give you a minute to copy and not understand. Oh, yes, you're right, Sarah. Thank you. So it should be xiyi, right? Yeah, thank you. Thank you. Okay. All right, if you have the code running, run it on the CO2 data, okay? Run it on the CO2 data, run the left rule, right rule, and then run trapz from NumPy. Let me make this a little bit bigger. We can't do the midpoint because what if the data is not equally spaced, right? It's not going to create new info if you interpolate, right? So you can't generate new info. You cannot create new info. That's it. You're limited by it. So you might as well just use the easier method. Okay. So I'm going to assume you did this. So let's do the left rule, discrete left rule, discrete left rule with the xi data and the y data for the CO2. We get 232 total metric tons per capita over those 50 years. And then the discrete right rule, xi, yi, is going to give you 233. And then if we do the NumPy, the trapz, okay, so trapz, it takes it the other way. It takes y and then x. So for trapz, we do yi, xi, and you get 232.8. So we're right in the ballpark. Yes? Oh, you have different data. That's right. So your data, let me see, where does your do this? Do xi minus 1. I got it to 2016, my data. Do xi. Okay, do this. That's fine. If you get different, yeah, so mine goes to 2016. Yours? 2012? Yeah, that's fine. It's the same data. I updated it on my end, but it's the same data. I just have more years, okay? So you got 222, but it's close enough to trapz, right? It's close enough to trapz. Yes? No? What is trapz giving you? Okay. 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 So right in the middle, right in between. Okay, very good. Okay, awesome. Wow, yeah, we did a lot. Okay, so now we have 10 more minutes. Yes, Yes. Because trap Z, it's a routine that they designed, and the designer wanted the y values first, right? So, if you look at the function signature, they need the y values first and then the x values next, right? We can design our methods to be the same, Lily, but it's just a convention. Just as long as you know kind of what you're using for what, right? Good point. Okay, so I have 10 more minutes. I still have to do the life hack, right? So Tanner is like waiting for us. Okay, I don't think I can finish everything today, but at least we'll get started. Trapezoidal rule. That's the infamous rule that NumPy is using, and you can use analytically and discretely, as you will see. The trapezoidal rule, the concept is you approximate f of x. What is the next order polynomial after a constant? It's a straight line. So a constant is a 0th order polynomial. A straight line is a first order polynomial. Agreed? So you take that interval a to b and you draw a straight line between a and b. All right? So now let's see your geometry skills. What is the area of that trapezoid? It's just the area under that line, right? So what's the area of the trapezoid? Average base times the height, right? Remember your geometry? Okay? Literally, you can evaluate this just using geometry. The area of this trapezoid is the average base, which is this base f of a plus f of b over 2, times the height, which is b minus a. So you get b minus a times f of a plus f of b over 2. Okay? And that's the trapezoidal rule. Now, what is powerful about the trapezoidal rule? What is powerful about the trapezoidal rule? I was going to make a statement, I'll turn it to a question. What is powerful about the trapezoidal rule? Think about the left point rule, right point rule. It does have that tendency, but that depends on the function, right? If the function is all kind of might be under the straight line, or go up and down, so you cannot really guarantee that. But there's think about discrete data. What is so nice about the trapezoidal rule? But compared to the midpoint rule, what is better about the trapezoidal rule? The what? We have the values. We don't need any new information in between. So if you have discrete data, all you need is the left point and the right point. You don't need any information in between. And guess what? It is more accurate than all the previous methods that we learned. Because the previous methods, they're just a constant. This method is straight line. It's not only more accurate, it's actually as easy to evaluate. You don't need any information in the middle. So it applies to discrete data and analytical functions very readily. Super powerful method. Okay? All right. So now I'm going to give you this question. I have this curve, y equal to x plus 3. And I'd like you to calculate the error in integrating y equal to x plus 3 on the interval 0 and 2 using the trapezoidal rule. So the exact answer is 10. So now I want you to use the trapezoidal rule to compute this integral. Or do you need to use the trapezoidal rule? Okay, why? So what's the error? 0. Why? Yes, exactly. So you're approximating a straight line with a straight line. That approximation is going to be exact. So the trapezoidal rule is going to give you, it was a trick question, right? So that approximation is going to give you the exact answer. So the error is 0, exactly 0. Okay? So if you're approximating a straight line with the trapezoidal rule, you're going to get an exact answer. Okay? Error is 0 because the trapezoidal is exact for a straight line. Okay. Now, what is the true error in integrating y equal a constant on the interval y, a and b using the trapezoidal rule. Okay, the Detroit Lions cannot answer anymore. They've exhausted all your answers. Okay, think about it. You don't need to do any calculation by hand. 0. I hear zeros. Why? Yes, a special case. A constant is a special case of a straight line. A constant is a straight line with 0 slope, right? So it's going to be exact for that. These are like the perfect exam questions, okay? And all the variations I can do on those, okay? All right. Okay, but that's critical thinking, right? Thinking about it this way rather than just running to the calculator. You can verify with the calculator, and you should, okay? All right. Simpson's 1/3 rule. Concept, approximate f of x as a quadratic. So we did a constant, 0th order polynomial. We did a straight line, 1st order polynomial. The next order of business is a quadratic, a 2nd order polynomial. So in this case, you need 3 points for the quadratic. So you take the 2 edges, but then you need a point in between. And that essentially immediately almost rules it out for discrete data. Because if you find a random point in between, it might not fit the polynomial correctly, right? The best way to do this is to draw the polynomial, pick the 3 points so that they are equally spaced, okay, on an analytical function. Now, when you do this, you pick point A, point B, and point A plus B over 2, so right in the middle. You fit a polynomial. You know how to do this. Because we have the x values, we have the y values. You can do interpolation, and you get the exact formula for that polynomial. And you integrate that exactly, because we know how to integrate polynomials exactly. They're very simple. And when you do this, you process the math, it gives you this beautiful, simple formula. Delta x is the spacing between the points. So if this is the interval b minus a, we picked a point in the middle, like the midpoint, right? So that's delta x over 2 and delta x over 2, okay? So b minus a over 2, that's what delta x is. So delta x is the distance between these 2 points here, equally spaced, right? And then you multiply that by f of a, and 4 times f of a plus b over 2. Just the fact that there's f of a plus b over 2 rules it out for discrete data, okay? But it's a way more accurate method than the trapezoidal rule, okay? All right. What is the error in integrating alpha x squared plus beta x plus gamma using Simpson's 1/3 rule?
0.
Yes! Why? Because that function is already a quadratic. And Simpson's 1/3 rule approximates a function as a quadratic, right? And to fit a quadratic on a quadratic, you're going to get an exact quadratic. That's what interpolation tells us, right? So the error will be 0. Okay, so what about applying Simpson's 1/3 rule on a straight line? Somebody said 1? 5, 0? 0. Straight line is a special case of a quadratic. What about applying it to a constant? 0. Because a constant is also a special case of a quadratic. If you do the interpolation analytically, you're going to get just zeros for the coefficients except for the constant. Okay? Finally, the last one is Simpson's 3/8 rule. Actually, I'll cover that on Thursday.